Hi everyone, I'm Blesson for Shaji, register number 25 PMC 124. I will be presenting on deadlock detection in operation system through the lens of graph theory. This presentation explains how operating system use graph theory concepts to model resource allocation and detect deadlock efficiently. In this presentation, I'll first introduce how resource allocation is modeled in operating system. Then I'll explain how deadlock becomes a cycle detection problem in graph theory. Next, I will discuss the algorithm used for detection and optimization techniques, like Banger's algorithm. Finally, I will explain real-world application in database and operating system. Resource allocation in operating system. Operating system allows multiple processes to run simultaneously. Each process may require system resources such as CPU time, memory, files, or input-output devices. Since resources are limited, they must be allocated carefully. The relationship between process and resources can be represented using a directed graph called the resource allocation graph. This graph model helps visualize weighting dependencies clearly. Four graph components. In the resource allocation graph, there are two types of vertices, process node and resource node. Process node represents running programs, while resource node represents system resources. There are also two types of directed edges, a request edge and allocation edge. A requested form a process to a resource shows that the process is waiting. An allocation edge from a resource to a process shows that the resource is currently assigned. This structure makes it easy to analyze dependencies. Deadlock occurs when a group of processes wait indefinitely for each other resources. There are four necessary conditions. They are mutual exclusion, hold and wait, no preemption, circular wait. The most important condition is circular wait. In graph theory, circular wait appears as a cycle in a directed graph. If a cycle exists in a single instance resources graph, deadlock is guaranteed. To detect deadlock, operating system use graph algorithms. Depth first search can detect back edges, which indicate cycles. Topological sorting can determine if the graph is acyclic. If sorting fails, a cycle exists. Strongly connected component analysis can also identify group of interdependent processes. These algorithms run in linear time of V plus E, making them efficient. Next, Banger's algorithm. Banger's algorithm is a deadlock avoidance strategy. Before granting a resource request, the system checks whether it will remain in a safe state. A safe state means there exists a sequence in which all processes can complete execution without deadlock. If granting the request leads to an unsafe state, it is delayed. This ensures stable and optimal resource allocation. Database systems. In database systems, transactions often lock rows or tables. If two transactions wait for each other, others lock, a cycle forms in wait for graph. The system detects the cycle and aborts one transaction to break the deadlock. This ensures database consistency and reliability. Operating systems. Modern operating systems such as Linux and Windows continuously monitors resource dependencies. The kernel internally constructs dynamic wait for the graph. If circular dependencies are detected, recovery mechanisms are applied. This may include terminating a process or preempting resources. This ensures the system remains stable and responsive. Conclusion. Deadlock detection is fundamentally a directed graph cycle detection problem. The resource allocation graph model system dependencies clearly. Graph traversal and optimization algorithms ensures that processes do not remain stuck in circular waiting conditions. This demonstrates how graph theory plays a critical role in maintaining operating system stability. Thank you.